Okay, so I'm just going to throw this S bigger and S interaction away. I'm just going to keep this guy and ask, what can I tell just from that? So, now we're just going to focus upon SS. Alright? Now, when I want to take a flow, I want to see how my system is behaving, right, as I integrate out stuff. Now, of course, you can do it any way you want, but a very convenient way to do it is to always make it look as similar as possible to the original system you started with. Okay? Because then it becomes very easy to compare the different couplings. Okay? So, what are the things that we know about the original system that we started with? Well, of course, it had some quadratic term, it had some mass term, it had some interaction term, but also it had a cutoff of lambda. So I'm going to rescale this now to make it a cutoff of lambda. Okay? So, let me define for you a k prime that looks like k times 1 plus dl. Alright? So when k goes from 0 to lambda times 1 minus dl, k prime will go from 0 to lambda. Okay? dl is a tiny number. Okay? Good? So 0 less than k prime less than lambda. Alright? Okay? So let me write down at least the kinetic part and see what happens. So let me call it S0 less. Okay? 0 means the quadratic part. So what will this be? There's of course a half. Now I have this integral up to lambda, right? Because it's now over k prime. So what was it? There was a d to the dk, but that's a d to the dk prime, right? Times 1 minus, or 1 plus dl to the minus d. Agree with that? Right? Alright. Then you have your phi tilde of k. What is k now? It's k prime times 1 minus dl. Phi tilde of minus k prime times 1 minus dl. Okay? Times k prime squared times 1 minus 2 dl. Right? Plus m squared. Just stare at that for a minute and convince yourself that it's correct. Okay? Yes. Good? So now let's proceed. So, let me pull out all the powers of 1 minus dl outside the square bracket and see what I have. So I have S0 less is 1 half. So I have d to the dk prime. Okay, this part now looks good. It looks like our original theory. Okay? Now let's see what else we can make look like our original theory. So, I have 1 plus dl. So let's see how many powers of it I have. Okay, so there's minus d powers here, minus 2 powers here. Right? So that is minus d plus 2 powers. Okay? And then I have this phi tilde of k prime 1 minus dl. Phi tilde minus k prime 1 minus dl. Times k prime squared plus m squared 1 plus dl squared. Okay? Alright. So now we've got a choice. Okay? So we can't keep both these terms invariant under this rescaling. So we got to pick. Okay? We can either keep this guy constant or that guy constant. Now clearly it's useless to keep this guy constant because this is the guy that is taking you through the critical point. Okay? So for the kind of critical point that we're interested in, it's much better to keep this number the same as in the original theory, okay, which was 1. Okay? So now what I want to do is I want to deal with all of this stuff. So let me define what I will call a rescaled field. So let me call it phi prime for just a minute, okay? So phi prime of k prime will be equal to 1 plus dl minus d plus 2 over 2 phi of k prime 1 minus dl. Okay? I have a rescaled field. Okay?
You are saying you want to make that constant.
I want to make it look the same as when we started in our original theory. Right? Remember what the original theory looked like? It basically looked like here. That's what it looked like. Except the 1 minus dl was missing. Right? I want to make it look like this without this 1 minus dl. That was the original theory, right? The quadratic part of the original. Okay? Good? So once I define that, what I find is this guy looks like the integral up to lambda d to the dk prime, and then I have a phi tilde prime k prime, phi tilde prime minus k prime squared plus m squared 1 plus dl squared half. So we've succeeded in making the theory look similar to what we had before, except it's not quite the same. We already have a RG flow. Right? What is this RG flow? The RG flow says that m squared has gone to m squared 1 plus 2dl. Okay? So let's see what this means. Okay, this means basically that if I had m squared equal to 0, that's a fixed point. You agree? Just for this. Okay, there's of course millions of other tuples, and we'll get to those in a minute. But as long as m squared equals 0, it will stay there, right? But if you deviate from 0, then it will grow every time you do RG, and therefore it's a relevant perturbation. So you know that this is a relevant perturbation. Okay? All right. Now let's go a little bit further.
So to make it similar, this is modified as limit must be lambda minus 1 minus t.
No. The original theory, before I started doing Wilsonian RG, had just lambda. Remember? So I want to make it as similar as possible to that original theory. So every time I throw away some degrees of freedom, integrate some of them out, I will rescale it again to make it look as it was before. Okay?
But I am working with this is smaller now. So we have to make it as same as this.
No. So remember, I want to make S smaller. The whole point of this rescaling was to make it look as similar as possible to the original one before I started doing RG. Right? Before I started doing RG, I didn't have small, large, nothing. Right? Yeah.
Here we started with exactly two constants. One
Yeah.
is m and another is lambda. But we could have started with three of them, right? We could have put a constant a in front of the kinetic term
Right.
and scaled the m here. Rather than
Exactly. So I could have kept the n constant, and I could have scaled the other one. That would be a good thing to do if the transition is something in which the sign of the derivative term changes. If the sign of that term changes, and that is your transition, then it's a good thing to keep the m term fixed and this term there. Okay, but the kind of transition we are looking for is not that. Because that transition involves having translationally non-invariant states that become favored. Right? If you take a minus of the gradient squared term, that actually says I want to change as fast as possible. Right? Okay, so now let's look at what this this rescaling does, it's some very complicated, messy looking thing, right? I want to see what this does to the fields in real space. Okay, that'll tell us something. So, let me define phi prime of x to be the integral up to lambda e to the d k prime e to the I k prime dot x phi tilde prime of k prime. Okay? Natural definition of phi tilde prime of phi prime of x. All right. So what is it in terms of the original fields? Let's now backtrack a little bit and ask ourselves what it looks like in terms of the original fields. Okay? So this guy, now I'll go back. So remember, k prime was 1 plus dl times k, right? So this is lambda times 1 minus dl, d to the dk, right? 1 plus dl to the power d, right? And then e to the power I, k dot x, 1 plus dl, right? And then I have this phi tilde prime, and now I'm going to put all of this stuff in there. So let me put all of it in there. So that looks like 1 plus dl minus d plus 2 over 2, right? Times phi tilde of k. You agree? Yes? All right. So I'm going to take all these powers out. So this looks like 1 plus dl to the power of d minus 2 over 2.
So inside this phi argument, will be replaced by k prime or minus q?
No, I'm just, so k prime times 1 minus dl is what we call k, right? So now I'm going back, I'm recasting everything in terms of k now. Alright? So now you look at what is sitting inside here is a Fourier transform of this at that location. Correct?